Okay, so hello everybody again. It's nice to be here, to be able to talk. I thank Matthew for the organization and Simon and Igor for inviting me to participate in this project. I'm going to give a brief overview of our project number 6, which is entitled Industrial Processes for Second Generation Ethanol Production and Cogeneration of Green Chemical Products. Just 3 slides to remind you about our guidelines. Our idea in this project is to evolve, to transform a sugarcane processing unit into a full-scale biorefinery. And this is quite a delicate problem because it is already running and based on low-value products. So it's if you imbalance the process, what is a good profit in a year may become a disaster. So they are very sensitive to changes. Also, we want to do that improving sustainability in terms of improving the energy balance. Currently it's 9-to-1. This is good, but 1 is going to become 0 in some time. Water balance is negative, and recycling soil nutrients. In my opinion, this is a great problem that has been overlooked in Brazil. This is another reminder. An average agro-industrial unit in Brazil is a plantation area of around 30,000 hectares, in which during the year you have to retrieve 1 ton of nutrients per hour in order to produce this biomass. You have, so this is the agricultural problem. You have also a logistics problem, harvesting and field operations, and the industrial conversion problem, in which you import water, you export CO2, you have vinasse, all the nutrients that were taken out from here will end up in the vinasse. You have solid residues, filter cakes, and so on. This is not actually a big problem. And you produce an average of 50 megawatts and 35 tons per hour of sugar, or 42 cubic meters per hour of ethanol. And this, just to give you an idea, this industrial unit costs about $200 million. This is the current production model. I'm not going to pass that through again because I showed you several times. Just I want to highlight that we have overlooked a problem here. This is new. The necessary dewatering process in order to burn the bagasse to produce electricity. Our evolved model would include a second generation process, a pre-treatment process, and a hydrolyzation process in order to free up sugars to be fermented, to increase ethanol production, okay? And a second process to recycle, especially to recycle nutrients from contained in the vinasse. Remember, we're bringing, I'm going back some slides. During the harvest period, we're bringing 500 tons per hour of biomass from the fields to the industrial unit, and we are taking out about 1 ton of nutrients, which is in this biomass, and it is contained in the vinasse here. So, in my opinion, this process here is mostly necessary to recycle nutrients, and if possible, to produce some added value chemical. This project, number 6, deals mainly with this model, this block here, and tomorrow I'm going to talk a little bit more about this one, okay? So the idea is to optimize a full unit producing first generation and second generation and electricity, and the optimization of this integrated process is what we call the Cinderella problem. I'm going to explain this little joke a little bit later, okay? Okay, so we're going to give a little more details about the 1G plus 2G ethanol and electricity production model. We actually made a macro mathematical model in order to be able to assess sensitivities and to see what would be the best composition of biomass in order to optimize production of ethanol and electricity. So we have several processes: Bagasse pretreatment, hydrolysis, juice fermentation, wine distillation. So this is the second, the ethanol production line with biomass depolymerization processes. Okay, the traditional line is you have a dewatering unit, you have a boiler, you have a thermodynamic cycle now to produce power and heat, which you can use in the process. Okay, so after that we can look inside each of these blocks and write some very simple equation. And just to explain you the things here, blue arrows are mass fluxes, okay, and red dotted arrows are energy fluxes. And mass input, or energy input, if you will, is contained in bagasse, straw, and sugarcane juice that comes from the extraction process, together with water. So let's go. Our pre-treatment process, we are considering hot water pre-treatment. So this is the industrial unit. You need energy only to rise the pressure and then to heat this mixture here. Thermodynamic equations are very simple. You need some energy in this phase here and then some energy in this phase here. As I said, thermodynamic equations are very simple. Don't bother with this. It's just an energy balance equations, okay? And what I really want to highlight is the dewatering problem. So in the process, this is more or less a typical unit. This is a 500 tons per hour diffuser to extract sugar, sucrose from sugarcane. And you have, at the exit here, you have bagasse with 80% humidity and less than 2% of sugar. It's very effective, this process here. Then you have two dewatering mills, maybe one, but most of the time we use two dewatering mills in order to reduce the humidity from 80% to 50%. And the amount of energy used in these two mills here is very big. So we were not aware of that before. Yes, that I think it's Igor Polikarpov. So the dewatering process is quite sensitive because it's actually very simple, the process. You have biomass entering here at 80%, then you have to squeeze it, you have to spend some time in order for the water to come out of this mill, of these row mills. And the problem is that, don't bother with the equations, it's just, but the problem is that at those processing rates, the amount of energy is very sensitive to variations in the properties here. For instance, fiber content usually is around 13% in the initial sugar cane, but it varies, depends on where you harvested this sugar cane and the species and so on. And it varies, and it may vary a lot. So 1.5 megawatts per 500 tons of sugar cane per hour is a lot compared, for instance, to the energy necessary to move, to transport all the amount of sugar cane that you have here. It's more than 100 times the engine that you have here. So it's quite important, this dewatering process here. And the amount of bagasse that you have to process for this typical industrial unit is around 150 tons per hour if you're going to dewater 100% of the bagasse. Okay? So the combustion process is also very simple. You have a boiler, I have several possibilities here. And the boiler will produce steam in order to run a power cycle. What's important here is the amount of water that you export. Remember, from 150 tons per hour of bagasse, you have 50% water content. So you have around 75 tons per hour of water. Plus the water that is generated in the combustion process. That means that you are exporting 100 tons per hour, let's say, of water. So it's quite a lot. It's much more water than the steam that you produce here. It's quite a lot. What we also do is to model Bagasse constitution and lower combustion heat. Actually, you can see its constitution like fiber, sugar, impurities, and water. Fiber content is around 45%, sugar is less than 2%, impurities is less than 3%. Impurities may be a bicycle, someone, I don't know, okay? Because it happens in your process must not be sensitive to this impurities. Let's call them like this, okay? And you also have water. And you have the combustion heat here, and, well, very simple, you have a formula in order to evaluate your lower combustion heat of your bagasse. You see that the water content is like having a negative combustion heat. And also, in this number here, you may recalculate this number for different contents in cellulose, hemicellulose, and lignin. So we can play with all these parameters. Moving further, the heat generated here in the combustion of not only bagasse but also straw and lignin, because this same analysis is done for the other solid fuels. And the idea is to generate heat which will power the power cycle. So this heat comes here, you have some work produced here, and those are the very, very traditional thermodynamic equations. Just to give you an idea, the pressure, the common pressure is around 50 or 60 bars. Okay? And the problem of the amount of water. The problem is that water reduces the heat of combustion, as I highlighted earlier, but also it increases risk of explosion due to incomplete combustion and reduces heat transfer efficiency, mostly due to fouling. Okay? You have this solid deposition on the tubes, and your heat transfer coefficients go down, so you start having a lot of problems. So the maximum contractual water content is 50%. There has been a lot of lawsuits related to this amount here. So we're going to consider 50%. Okay, that's going on. So I omitted some of the equations regarding other processes because, well, that's not the idea. The idea is just to show you the results, because we want to play with the parameters. I'm going to play here, I'm going to put my finger there and choose, I'm going to send 50% of the bagasse to produce ethanol together with sugarcane juice to increase ethanol production, and 50% to be burnt to produce electricity. So if I increase the amount of bagasse being sent here, I increase the electricity and I decrease ethanol. That's the whole idea. I can play with this parameter. I can play with the constitution of bagasse. I can play with the boiler pressure, for instance, and see and try to find a set of parameters which will optimize my overall process. Okay, so let's just understand in a little more detail what we mean by optimization. So the idea is that if you increase electricity, you decrease ethanol production. Okay? If I send 100% of the bagasse to be burnt in order to produce electricity, I have a maximum quantity of electricity. If I send 0% to produce electricity, I have a minimum amount of electricity being produced from straw, from lignin, and I have a maximum production of ethanol. Okay? And the line that links these 2 points can be constructed from our model. Okay? So the idea is, if I reduce from 100 to 90%, that means 90% of the bagasse is being burned and 10% is being used to increase ethanol production. So that means that you're going to have your operating in this point, and you have, let's say, a gain of production in terms of electricity and a gain of production in terms of ethanol. So what we want to optimize is the overall gain of production. Okay? Actually, this is a 2 degrees of freedom optimization problem, which is a little bit more complicated. So what we did for the moment, we generate an artificial optimization parameter, which is the product of these 2 relative gains of production. Okay, so the formula is this. So in this axis here we have this relative overall gain of production, and in this one we have the amount of the bagasse fraction being burnt or being hydrolyzed. And we start constructing these curves for different sets of operation parameters. For instance, fiber content, boiler pressure, and so on. And what's interesting to see is that our best curves, because, well, these points here are the tops here, are the best operation points according to this optimization criteria. Okay? And the lower the water content, the higher this point is. So what this very simple model shows is that it is a lot more advantageous to have biomasses with less water content. So this is something very interesting. The problem is, what I see, is that this is being done in terms of production. Okay? If we did a full 2 degrees of freedom optimization problem, probably we would reach the same conclusion. But what we should be able to do in the near future is to make this optimization in terms of money. But the problem is, it's very difficult to assess the costs associated with second generation ethanol production. Because, well, you know, we don't have enough experience at those processing scales. We did other tests, and some conclusions can be highlighted at this point. For instance, the sensitivity or the sensitive processes, which processes are more sensitive than others, which would be this is a very interesting information to decide where to focus research and development, for instance. Pretreatment and hydrolysis efficiencies are very important. If you play with these efficiencies in the model, you see that those curves change a lot. So it still has to be, a lot of work has to be done here, at those scales especially. And another problem, fermentation at large scales is still the less efficient process, in practice I mean, for sucrose conversion as well as for yeast cultivation, okay? Also, using less water in sugar extraction would be great, okay? Converting into other biochemical compounds, we are studying this under this project. I didn't have the time to show you, but we are designing a diffuser for acacia, and also we are designing a photobioreactor for vinasse processing. I'm going to talk about this tomorrow. And what I was saying is that to have a low water content is very important in the overall process. So if second generation ethanol becomes competitive, I mean, if the costs are realistic compared to other possibilities that you have to exploit biomass, maybe we should be planting eucalyptus instead of sugarcane in Brazil. I don't know. So the problem is to optimize fiber, sugar, and water content in the plant. So it's a great problem for plant breeding. I'm going to skip this transparency because I'm going to talk about them in the seminar. Because for each of these conclusions, we have some actions that were taken. So in order to optimize, to have a better and more efficient fermenter, we are making some studies that we're going to talk about tomorrow. So this is what this transparency is related with. And also the 10 cubic meter photobioreactor, which I'm going to show you tomorrow. Just to conclude, the story about the Cinderella problem is that, remember, the overall problem can be divided in three stages. You have agricultural production, you have logistics, you have industrial processing. And, well, the agricultural practices or the agricultural problem and industrial problem are quite rigid, actually, because you have here land use problems, you have costs related to the industrial equipment. Remember I said they are very resistant, recalcitrant to changes in this industry, because if you make a small mistake, it can be a great problem, and you're going to lose a lot of money. So the problem actually is to finding biomass composition and physical properties best suited for agricultural production and industrial conversion. So it's like the Cinderella problem. The agricultural production and industrial conversion is rigid, so it's difficult to make changes. So in Cinderella is the biomass. So what would be the best Cinderella for our crystal shoe? Okay, thank you very much.